It's hard enough for someone intellectually gifted and experienced to attempt to explain something as difficult as quintic insolvability. So why the heck would a certifiable non-genius with little to no training in complex analysis and algebraic structures attempt it? In other words, why would someone try explaining something they have no clue about? Doesn't that just further confirm their stupidity? Maybe so, but I actually do have a bachelor's in math, and I worked hard on these ideas for almost a year, asking my Microsoft Bing Copilot tutor hundreds of unusual questions, because despite its unreliability, it was far cheaper than a professor and far more accessible than textbooks. So I'd like to make a bold attempt to express some of what it revealed to me, even if I risk a lot of incorrectness in the process. And if I happen to be lucky enough for some of these ideas to mesh somewhat with reality, maybe it will be of some use to somebody. I find that the great minds that grasp this quintic material easily speak with ideas and language that's too difficult for most people to understand. So perhaps someone else really struggling with this material is who another struggling student needs to hear to serve as some sort of intermediate step to deeper understanding, even if the intermediate step is greatly flawed. I guess I'm like Clark Griswold from the National Lampoon Vacation movies, where I can't tell if the ambitious work I'm doing is quality or garbage. But at least I mean well. The intent isn't to provide a solid, irrefutable proof, but a very rough but hopefully intuitive map of ideas. Think of it as a fun, magical, mathematical mystery tour. Anyway, that's enough background for what's intended to be accomplished here, so let's move on. I want us to start by looking at the quadratic formula, which I believe is still in the high school curriculum. Something fairly understandable to a lot of people, even though it's still a bit complicated to look at. This formula is one expression, but usually gives us two answers because of the plus and minus sign. But we can make it look more like one expression by manipulating it with some algebra. We can manipulate it further with something handy called Vieta's formulas, which express the coefficient of the polynomial in terms of its roots. This is still the quadratic equation, but what's interesting is that we can see that if we put root r1 wherever we see root r2 and put r2 wherever we see root r1, the equation still stays true. A big part of this is because Vieta's formulas are highly symmetric. And right now I'd like to point out that while the quadratic formula is true, there's another formula that is true as well, expressed in what I would call linear factors. Now, if a hypothetical quintic formula existed, it would follow pretty much a similar format, where it would have to be true in a formula involving its coefficients and in a formula involving its linear factors. Here, the coefficients of a hypothetical quintic are represented in terms of roots. We see the symmetry of Vieta's formulas even more here, but more than just an idea of looking repetitive, symmetry in polynomials means possessing the ability to swap two roots without altering the truth of the equation. Symmetry in equations is kind of interesting, and Aleph Zero's outstanding video on the fundamental theorem of Galois theory gives great visual demonstrations of it. But I also think symmetry in sentences can be interesting too. Take this sentence, for example, one you might see someone using in a church. Now you can switch the words everybody and anybody, and I think the sentence still works. But if you're like me, you can't memorize this thing very well, and you'd probably switch the words nobody and everybody, and that won't work at all. This would mean the sentence is symmetric sometimes and not symmetric other times. In other words, it's partially symmetric. Well, in any case, now that we're talking about symmetry, we are at the part of Quintic insolvability where permutations enter the picture. We may or may not be able to appropriately permute the roots of a formula. If we can't, then the formula is invalid. A quintic would need to be valid whether we put R1, R2, R3, R4, or R5 in the standalone part. Any of those roots need to work for the formula. Everything else should maintain its symmetry because of the symmetric nature of Vieta's formulas. So the formula would have to be at least partially symmetric, or some of the roots could be switched. But not only would such a hypothetical formula have to be valid in order for us to have a quintic formula, but the much simpler linear factor formula would have to be valid as well. And in this case, every possible permutation of roots would have to be allowable, since the stuff in parentheses is being multiplied and order of multiplication doesn't matter. Every permutation would have to be allowable also because we're looking for a formula that's general, and we can't really narrow down the permutations unless we get more specific. Aleph 0, as I've already mentioned, has a wonderful video on root swapping and symmetry that there's no way I can improve upon, so instead of touching on that subject, I'll move straight to the idea of how complications arise when attempting root swapping with nth radicals and the multiple values of their conjugates, particularly nested nth radicals and their conjugates. Now, the conjugates of the inner radical of a nested radical you can swap freely, to my knowledge, without altering the existing conjugates of the outer radical. But it should be easy to see that if you swap one of the conjugates of the inner radical with a totally different root of the polynomial outside of either of the radicals, you're going to most likely get some totally new value that wasn't a conjugate of the outer radical to begin with at all. So you're doing a lot more than just trying to swap roots when you start messing with the conjugates inside a nested radical. So when we have nested radicals involved, we need to make sure that every time we permute the stuff inside the larger radical, the stuff inside the smaller radical stays a permutation of the stuff inside the smaller radical. And this, I believe, is the main idea behind normal subgroups. Normal subgroups are usually defined by, if you do a larger group operation, a normal subgroup operation, and then reverse the larger group operation, the stuff inside the normal subgroup never leaves the normal subgroup. This definition has never been comfortable for me. It just isn't intuitive. But I believe there can be a less efficient, more cumbersome definition that is much more intuitive. A normal subgroup needs to fulfill these 4 criteria, where n is an element of the normal subgroup and g is an element of the group itself. These 4 criteria show that no matter what sort of available permutation you do to the group, and no matter what order you do it in, the elements that are in the normal subgroup will never leave that subgroup, ever. I think that's much clearer than the traditional definition of a normal subgroup, but the traditional definition is much easier to test for computation purposes and involves much fewer calculations. It's a case of what's efficient versus what's intuitive. So I think a better way to think of a normal subgroup is that when you take a group and arrange it in all possible ways, no matter what way you arrange it, if all elements of a subgroup stay in that subgroup, then it's a normal subgroup. And I think that's what we had to do with nested radicals, making sure that every time we permuted the stuff inside the larger radical, the stuff inside the smaller radical stayed a permutation of stuff inside the smaller radical. Again, I'm taking a big chance here on my accuracy because I don't know if the stuff I'm saying about nested radicals relating to normal subgroups in this manner is mentioned in any textbooks, but it's the best path my mind can come up with. If nested radicals are related to normal subgroups in this way, then to be able to write expressions in terms of radicals, you've got to have normal subgroups. And I really hate that, because I've tried desperately for at least 6 months to avoid dealing with normal subgroups, hoping to deal with abelian quotient groups or anything else instead. But I couldn't get away from normal subgroups no matter what I tried. Now that normal subgroups have entered the picture and have been tied with radicals, we can think of repeatedly nested radicals bearing some relation with a tower of normal subgroups. And every time you permute the outer conjugates of a portion of the tower, everything inside would have to stay in its own area and not venture out. So for all of this to happen, you need to make sure the permutation groups of the inner conjugates are normal subgroups of the permutation groups of the outer conjugates. Provided that all of that's correct, now you just need to take a look and see if the general quintic can fit this criteria. We already know from earlier that the general formula with linear factors leaves us all possible permutations of 5 roots to be considered. This is called the S5 symmetric group. Now we sketched the idea that a chain of normal subgroups is required for the conjugates of nested radicals to stay in their own lane. What's nice is some of the permutations that make up the elements of S5 conform to this criteria. The problem is not all of them do. All permutations must for a general formula to be possible. Every permutation in S5. But some don't. Some have a group of permutations known as A5 in the chain. And once you hit that group, you're done. A5 is a group with no normal subgroups. And you've probably already heard that's why there's no general quintic formula. But how do we show that A5 has no normal subgroups? I didn't look into that very much while I kept beating my brains out trying to make sense of all the other normal subgroup stuff I just mentioned. Well, if the 4 criteria defining a normal subgroup we mentioned earlier are not fulfilled for any particular element in the group, it's obviously not going to have a normal subgroup. But this A5 group does have sets inside of it that fit the 4 criteria. 5 different kinds of sets, which are typically referred to as classes. The formal term is conjugacy classes. The classes are as follows, from what the fallible yet helpful Microsoft Bing Copilot tells me. I do not know how cycle structures form these particular classes honoring the 4 criteria, but worst case scenario, I imagine you can test the elements individually to find out. Of course, it would be awful cumbersome to do. Thankfully, there are a lot of resources that discuss how cycle permutations work, because I'm somewhat ignorant about them, and I don't have time to go over them now anyway. Well, this division into classes doesn't seem to show at all why A5 can't have normal subgroups. It looks like it has 5 of them. But the thing about conjugacy classes is that you can't have a chain of them like you can have a chain of normal subgroups. The conjugacy classes are already maximal, so to speak. There are no subconjugacy classes of subconjugacy classes like there are normal subgroups of normal subgroups. But it's a different story if you have a combination of conjugacy classes. Those can make a group with another group inside. However, you also need the size of a subgroup to evenly divide the size of the group. This is Lagrange's theorem, and it's another thing I don't know very well. But it says with permutation groups, the number of elements in each subgroup must divide the number of elements in the entire group. You can practice this with the permutation group of 3 objects. There are 6 possible ways to permute 3 objects, so there's 6 elements in the permutation group. If you take any 4 elements of this group and try to form a subgroup out of it, you'll get a feel for why Lagrange's theorem is necessary. The properties of the subgroup will not match the properties of the whole group. You'll have a problem with inverses or with closure or something like that. So a normal subgroup needs to do 2 things. It needs to be a combination of conjugacy classes, and the number of elements in it needs to divide the number of elements of the entire group. This is how we can test to see whether A5 has any normal subgroups. We can see if any union of its conjugacy classes divides the number of elements in the group, in this case 60 permutation elements. Well, the identity element needs to be in the group because, to me, it makes no sense to have a group of permutations of stuff that doesn't include some kind of original order to permute in the first place. The formal term for a group always includes the identity element anyway, and again, if you play around with a group like the permutation group of 3 elements and try to not include the identity element in the subgroup, you run into problems. We already found out how many elements are in each conjugacy class: 1, 12, 12, 15, and 20. And we also know all the divisors of 60. They are 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. Do we have any combination of the one identity element and the other totals of the conjugacy classes that will add up to a divisor of 60? 1 plus 12 is 13. 1 plus 12 plus 12 is 25. 1 plus 20 is 21. Man, I don't see any way to get a union of conjugacy classes that includes the identity element to divide the number 60. And that's exactly the case. That's why A5 has no normal subgroups. And since there are permutations of the S5 group that can have A5 as a subgroup, that means not every permutation of S5 can be represented as a chain of normal subgroups. It means we can't always get this linear factor equation to be true, and therefore we have no Quintic formula. That was a mess, and was a lot of stuff to try to figure out, much less try to get it all correct. I was hoping to go into detail of how someone actually found a Quintic that was unsolvable using methods like Eisenstein's criterion, but that wasn't discovered for a while until after the Quintic was already proven unsolvable, and I haven't learned that stuff. We've already done enough hard math for one day. At least I have. I'm tired. Plus, I did several major revisions to this script because I kept finding major errors over my months of work on it. Might still have major errors, of course. In any case, I'd rather publish it at this point with errors than do another revision. Otherwise, I'll go insane and start thinking I'm in a David Lynch movie. I think at one point I did have a somewhat alternative approach where I argued that we start with an abelian group under a single radical sign and build up a field with nested radicals where each intermediate field would have all the conjugates of the outer radical in it, and each expression would have the new conjugates in the intermediate field, also forming an abelian group. So stuff could be written in radicals just from abelian extensions. I believe the approach is correct, but I had a harder time trying to show A5 as a simple group with that approach. Hopefully the mathematical community doesn't tear me up over this unpolished content, especially since I had to rely off Microsoft Bing's AI Copilot as a tutor, but I thought I'd post it anyway because I think there may be something valuable in it somewhere, and if there isn't, I guess sometimes it's better to ask for forgiveness than permission. But if I'm anything like heel wrestler superstar Billy Graham, I won't even ask for that.